Okay. Okay, that means this week we'll focus on the last two sections in chapter 11, 11.10 and 11.11. And we will talk about the Taylor and MACLAURIN series. That we do have a new infinite series, new power series, which we call Taylor and MACLAURIN. Of course, that's the names of the mathematicians. Okay, let's see what we have. In the last week, the previous week, we did power series representation, okay, for some type of function. And one of them was the most common, which was the geometric property. We used the geometric summation to get the power series representation, because we remember, like all of the scientists, all of like lots of application use the power series representation, because we all like power functions. Okay? Power functions are like polynomials, which we can replace exponential function, logarithmic function, trigonometric function with the power function, which are much, much easier to compute things, to deal with it. Okay, but because we were using the geometric property only, we were a little bit limited. I can write down this, because we remember only function of 1 over 1 minus x could be rewritten as a power series starting from 0 at infinity, and it's just x to the power of n. Right? We remember this. And if x is different, of course, we can change x. And an interval of convergence is from -1 to 1. That's, we can only use the x from that interval. And having a similar rational function, we can like move numbers, we can rewrite function and fit to this formula. We can also differentiate or integrate, and also we can change the function, but still using this power series representation. That means what we will do today, we will try to get power series representation for any function. That means, let's say, for example, e to the x. Okay, what is the power series representation? I can see function e to the x, I would say, has nothing to do with this rational function. Even if I will integrate or differentiate, I can't like go through using just this tool. Or let's say one of the trigonometrics, sine of x. Okay? That means we still like to have, instead of this type of function, the power function representation. That means, let's see, I can maybe write just the general formula, c sub n x minus a to the power of n. And of course the same for this one. X coefficient and x minus a to the power of n. And we remember a is a center of an interval of convergence. In order to find an interval of convergence, most likely we will use the ratio test. Okay, that's what we have to do. X minus a, x minus a to the power of n, it's always the part of this power series representation. But what we will do, the coefficient c sub n, we have to like link to the function. We have to get some connection, like how this coefficient, it's going to be defined if function is e to the x, or if function is sine of x, or any different types. Right? That's what we will find some connection. And then we can probably find the power series representation for any function. Okay, that means let's start. Okay, that means that's what I just said. Let's just start by having this general formula. Okay, and we would like to connect the coefficient c sub n with function. Okay, that's mean we will do a few things. I will just double check we all understand I'm just looking at different screen. We all understand the expanded form. If I substitute instead of n 0, I have c sub 0, and this will be 1. And instead of n 1, I have c sub 1 and x minus a to the power of 1. And then 2 and the square, 3 and cube, and so on. And of course, this is x minus a less than radius will give me the interval of convergence. Okay, let's do something. Of course, we have to remember, now I will show you how to derive some formulas, how to get some connection, but the only thing that we have to remember it will be the final formula, the output of whatever I'm trying to show you now. Okay, let's see. I will try to do something, of course, like to get some connection, as I said. And what I will do, I will start with substituting instead of x, a. Okay, and let's see what's happened. That means if I will actually take this, okay, and if I will substitute instead of x, a, we can see this will be a, this will be a minus a, 0, 0, 0. All of the terms are gone except the first one, c sub 0. Okay, that means f of a is a 0, is c sub 0, c sub 0. Okay, that means you can see, probably it's a little bit weird, but at least I have some connection that if I substitute a, f of a, the value of the function at a, it's giving me c sub 0. Okay, just one thing. Let's look at the next one. Oh. Okay, that means this is one more time my function. I skipped the sigma notation. Okay, that means I have just the expanded form. And if I did substituting again a, I'm getting c sub 0. Okay, now what I will do, I will differentiate this power series representation. Okay, I will differentiate, and we remember how to differentiate. That means I took this first line and I found the derivative. Derivative of the constant c sub 0, 0, gone. Derivative of the linear term c sub 1 times x is just c sub 1. And then derivative of x squared is 2x, which we can see we have 2 in front and copy everything. Derivative of x cubed and all of the constant around will be 3x squared. And then derivative of x to the power of 4, 4x cubed, and so on. Okay, that we can see, I only differentiate. And you can probably guess what I'm doing. I will try to substitute a to the first derivative. That means instead of x, a, that means we can see 0, 0, 0. F prime at a is c sub 1. Okay? And now I will try to keep working this way, which means I will differentiate again. Let's see. The second derivative, the same, just the differentiation of the first derivative. C sub 0 is gone. 2 times x will be just 2, keeping the constant c sub 2. We have 3, but we have x to the power of 2. Derivative of x to the power of 2 is 2x, and just copy the existing constant. X to the power of 3 is 3x squared, and keeping 4 c sub 4. And then the same thing. X to the power of 4 will be x to the power 4x to the power of 3, and I think 5 was here. Okay. Yeah, you can probably pause the video and think about the derivatives, but that's how it is. The same thing, instead of x, a. All of the terms with the x being a, gone. That means my second derivative at a is 2 c sub 2. Because what I'm trying to do, I'm trying to get the connection. That means connection between a function, or maybe even the derivatives, and the coefficient. That means, let's see. F of a is c sub 0. F prime at a is c sub 1. F double prime at a is 2 c sub 2. Let's take one more, the third derivative. Okay? You can pause the video and you can probably double check everything is correct. And putting a instead of x, this is gone, and the rest of the terms is gone. The only thing that will stay will be 2 times 3, c sub 3. Okay? And now I want to get a pattern. That means the first derivative was 1 times c sub 1. The second derivative is 1 times 2. The third derivative is 1 times 2 times 3, c sub 3. That means the fourth derivative will be 1 times 2 times 3 times 4, c sub 3. Okay? That's all c sub 4. I have to keep my, that means now the nth derivative will be, can you actually tell me what this formula is? 1 times 2 times 3 times 4, or the previous one, 1 times 2 times 3, 1 times 2, n factorial. Thank you, Anthony. That means my nth derivative of the function, it's simply defined this way. Nth factorial times c sub n. Okay? That means this is actually what I can do. I can take this equation and solve for c sub n. This one. Okay, solve for c sub n, which means just divide. I just divided the whole equation by n factorial. Okay, and this is giving me actually really good connection between the coefficient in my power series and the function. That means I have to just find the formula for the nth derivative of the function at a, at the given point, okay, and divide by n factorial. And then I can find the power series representation almost for any function. Okay, that's important formula. Let's take this formula and substitute to the sigma notation, to the power series. Okay, that means if this is just like 0, which means nothing, means the value of the function. Just here, I just have. And the 0 factorial, of course, we remember is 1. Just for the computation. Okay, that means let's see. Okay, that means this is one more time the power series formula, and we want the power series representation, and I'm taking the new thing and substituting here. And then we have this. Okay, that means this, the bottom box represents the power, this is the power series representation for any function. Of course, we still have to compute this, the first derivative, the second derivative, and so on. But we can have the power series representation. Okay, and let's see the expanded form. That means if n is 0, it's simply the value of the function. If n is 1, we have first derivative 1 factorial x to the power of 1. If n is 2, second derivative 2 factorial x to the power of 2, and so on. Third derivative 3 factorial x to the power of 3, and so on. Okay, that means this is the expanded form. Okay, few things, and we will start putting this in action. Oh, okay, that means I thought that I have on my next slide. That means this formula, the power series representation for the function with this new thing, the c sub n being defined like that, we will call Taylor series, because this was developed, this was discovered by Taylor. He is the mathematician. That's the reason that we naming this Taylor series. Everything is the same, it's still the power series, but with this specific formula for c sub n. Okay, okay, I have something on the next slide. That means we can see one more time, that's the Taylor series, and the quantity A could be any quantity. That means I can try to find the power series representation for the function, and we can, depends, we can pick the center. We can say, okay, I want the power series representation for my function, centered at 1, centered at 2, 3, 4, 5, and negative numbers. We can pick the value, okay? But what we also have, we do have a special case of the Taylor series, and the special case is when the center is 0. That means when the center is 0, of course, I can substitute 0, but we're not really writing x minus 0, it's just simply x, okay? That means this is also a Taylor series, but centered at 0. And we also have a little bit different name, the special case of the Taylor series. Oh, I see. I hear some. Okay, thank you, Samuel, for muting your microphone. Okay, that's mean the. Let me show you. Oh, okay, that means this is actually if the center is any number, even if it's 0, we can still say it's Taylor series, but we call a special case of the Taylor, and this will be the MACLAURIN series. And the Taylor series is named after English mathematician Brooke Taylor. The MACLAURIN series is named also the British, I can say, Scottish mathematician Colin McLaren. Okay, and we just call a special case of the Taylor. That's we do have a MACLAURIN, which is centered at 0, and Taylor. And actually now, if I will again take my rational function 1 over 1 minus x, right? We know the power series representation is just x to the power of n. Can you tell me what is the center of this power series? It's 0. That means actually, of course, we didn't really use the C sub n formula, but we can also say this is MACLAURIN series, because it's centered at 0. Theoretically, everything what is centered at 0 we can call MACLAURIN. Just in case if we end up like having this name. Okay, but let's work. That's me now. What we will do? Okay, still few things. What we have. Just the definition one more time, Taylor polynomial, that, I mean, hang on, because Taylor polynomials are 11.11 section, okay. But let's just see this. Because what we will do, we will try to find the power series representation for the function, and we will use, of course, the Taylor series, which means we will use the new formula, which we have here, the nth derivative at a over n factorial. But what we can also do, Taylor series means like that's the formula for the Taylor series, okay? Which means we will have n infinity. We have infinitely many terms. But we can also take, like, we can cut these terms, and we can say, I just want like 100 terms, a finite number. Okay, that means as soon as I'm taking finite number of terms, like while I'm expanding this, we will call this Taylor polynomial. And depends how many terms I'm taking, like what is the n will give me the degree, because we know is x to the power of n. If I will say like x to the power of 2, let's look at this one. Yeah, that's the expanded form. This is at 0, but doesn't matter. We can see if I will just cut here, this is the first degree, because it's x to the power of 1. If I will cut just here, this is the second degree polynomial, because n is 2, x to the power of 2. And then x to the power of 3, 4, and 5. That means taking finite number of terms, I'm actually of the Taylor series, I'm creating a Taylor polynomial. And I can also say that some of the functions we can approximate by the Taylor polynomial. That means this is a Taylor polynomial, okay? Which we can call like a partial sum. Like, do you remember, like instead of taking the entire sum, I can just take the partial sum. That means for this one, Taylor polynomials will be a partial sum of the entire expansion. Okay. Okay, I have also this. That means this, we can see infinity. That means this is the entire series. And I can take Taylor polynomial, which means I'm cutting. And then I have something more, which we will call like remainder. We remember like a remainder. That means approximating a function by Taylor polynomial, degree n. Okay? We always have a little bit of like error, okay? Which of course we will have the remainder. Okay? Hopefully we will try to evaluate this remainder like we did in the alternating series test. Okay? But that's we can see the partial sum and the remainder. Okay, probably just common sense. Oh, I do have some explanation. Let's see. Okay, that means this is just the finite number, okay, from 0 to n, and this is from n plus 1 to infinity, the rest of them. Okay. And one more time, I can actually copy this. If I'm taking this approximation, okay, I'm always assuming that my remainder is like almost 0. Yeah, it's like approaching 0, and then I can have my Taylor polynomial as a representation of the following function. Okay. Okay. Another theorem, but this is almost the same thing. Actually, that's what I just said. If we want a function, yes, if the function is rewrite as a Taylor polynomial plus the remainder, which is actually the Taylor series, okay, then t sub n is the nth degree Taylor polynomial of the function f at a, and the remainder is 0. That means we will take the polynomial, and the rest of the terms just behaves at infinity. It behaves 0. I mean, the remainder approaches 0. Right? Then function is equal to the sum of its Taylor series. Okay? And then we can, of course, we still have infinity, but we can say if the rest of the terms are like becoming 0, then we can say that the function has really this representation, Taylor series representation. Okay, I just wanted to make sure that we all know that the rest of the terms will go to 0. And we will not prove this because it's not easy to prove this remainder. We will always say, okay, this is my power series representation, and this works because the remainder definitely goes to 0. Okay, that's a little bit of theoretical part. Okay, let's start working on this. Okay, that means I have the first question. Find the MACLAURIN series of the function e to the x and its radius of convergence. Okay, that's we can see. I call MACLAURIN. Also, the equivalent question will be find the power series representation. Okay, like we did last week. Find the power series representation. But since I'm asking for the MACLAURIN one, I want center to be 0. Okay, and what I did, I have my formula for the MACLAURIN series. We can see it's the nth derivative at 0 over n factorial x to the power of n. And then I have to find the value of the function at 0. I have to find the value of the derivative at 0, second, third, and so on. And if we're lucky enough, and if we can find a pattern, if the derivatives behaves nicely, we will get this form. But sometimes we will not get the nice sigma notation. Sometimes it's enough to give like this expanded form. Okay, but let's see. I have a little table which I will use. This will be n. This will be nth derivative, okay, at x. And this will be the nth derivative at 0. And n will be 0, 1, 2, 3, and maybe 4. Oh, I can't write 4 because it's end of my slide. Okay, 0 means just the value of the function. That means f of x is simply e to the x. 1 means the first derivative. Can you tell me the first derivative of e to the x? E to the x is quite nice function. Of course, thank you, Anthony, is e to the x. 2 means the second derivative. What's the second derivative of, yes, Samuel? I don't know if you, that's the first question, that's the first answer, but what's the second derivative? Is the derivative of the first derivative. That means it's e to the x, right? And what about the third derivative? The third derivative, of course, same, thank you, of course, e to the x. That means now, I think we are lucky, because if I will ask you for the nth derivative, the nth derivative is also e to the x. So simple. And now let's substitute 0. E to the 0, 1. Of course, e to the 0, 1. E to the 0, 1, and so on. That means the nth derivative at 0 is just 1. Okay, that we can see I can substitute, I didn't type this. I can have my expanded form if we like. That means f at 0 is 1. And then this one will be 1 over 1 factorial x. 1 over 2 factorial. Actually, I can maybe get the values. 1, 2 factorial is 2. 1, 3 factorial is 6. Maybe one more. 4 factorial is 24. And so on. As we do have, we can see, I only typed like the 4, I mean x to the power of 4. That means I can think that this is the 4th degree Taylor polynomial. But since I have 3 dots, I'm thinking about the power, I mean the entire Taylor series. Actually, I should say MACLAURIN because it's centered at 0. Okay, and let's come back to this one. Since I know the nth derivative at 0, 1, I will have my e to the x function, I mean power series representation, 1 over n factorial x to the power of n, which I can write starting from 0, ending at infinity, x to the power of n over n factorial. Okay, that's me now. This is because what we will have, I think today we will have 3 or 4 formulas. This is the first one because we will probably not really compute this all the time. I think we have to just like kind of memorize this. That's mean e to the x has this power series representation. And whatever I said before, like about the remainder will be 0, definitely. That means this. This is the correct power series representation. Okay, and what we will have to do in order to find the radius of convergence, we have to use the ratio test, but I will skip this because I think you can do it, but I can tell you this works for all of the numbers. Radius will be infinity. Let me check. I think I have my ratio test on this side, on the next slide. And by the ratio test, we're getting 0. 0 is always less than 1. Then all of the numbers will give me convergence. Okay, and we can double check. E to the x is defined like that, and I do have the expanded form, but I did on the other side. X over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. Okay, let me come back to this. That means this is the formula to remember. Okay, we have e to the x, and we can see we didn't use the geometric one. We use the MACLAURIN formula. Okay, e to the x, check. Let's see another one. Okay, I do have, let's see, e to the x is defined like that. Now, if I will give you, not the power series because x is gone, if I will give you something like that, just the infinite series, you probably remember before the exam too, summation from 0 to infinity, 1 over n factorial. Do you think you can give me the sum of this? Of course, we can prove that it's convergent, maybe by comparison, or maybe by the ratio test, because we do have a few tools. But previously, we were only like looking if it's convergent or divergent. If it's convergent, we were not really able to find the sum. But what do you think? Do you think this looks similar to this one, to this formula that we just learned? Like if I will add maybe n, that's mean what I change. Looking at this, and of course, knowing that this is e to the x, what I change in this formula, what is gone? Yes, the x is gone. And what is in place instead of x? What do you see? Instead of x, underneath, yes, it's just 1. That means what I have to do, I have to put e to the power of 1. Okay, that means, and I can just say e. Oh, I think I typed this e. Okay, that's, you can see that's how we can kind of test if we recognize the formula. That means 1 over n factorial could be recognized as a 1 to the power of n. 1 to the power of n number is 1 over n factorial. Okay, that means this is e. Okay, now quite neat. We know the sum. We will be keep adding 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and the sum will be never greater than the value e, 2.7. Okay, what about this one? Can you tell me the sum of this one? Just the infinite series? 2 to the power of an e squared, of course. Did I type this? Yes, because we can see instead of x, we have 2 squared. Okay, and I think I have one more. What about this one? This one is a little bit tricky, but it's still the same. I'm still testing the same formula. It's it's 1 over, oh, no, something is, okay, let me add this. It's not 1 over e cube. Did I type this? Okay, I didn't type. Let me do this. Because what I need, I still need to see just n factorial in the denominator. We can see the general formula. And I can maybe lift everything. Yes, that's correct. Thank you, Samuel. You were actually before me. I can lift the entire fraction up. That means I have 1/3 to the power of n. That means instead of x, it's 1/3. Cube root of e. Yes. Yeah, it's nice to like see how the formula. And I have one more. You probably also remember from the infinite series. That means this one. What's the sum of this one? This one should be easy. -1 to the n over n factorial. That means what is the sum of this one? Oh, what we have instead of x? Yes, e to the, thank you, e to the -1, 1 over e. Okay, but we can see. We got the formula through the new Taylor series or MACLAURIN series, and we can play with it. Okay, let's learn another one. Okay. Find the Taylor series for the function e to the x, but not at 0, because at 0 was the MACLAURIN one, at 2. That means, do you think, what will be the nth derivative of e to the x at 2? Because that's what we need. We need, again, this is supposed to be 2. I think I copy. And this is supposed to be x minus 2 to the power of n. Okay, that's what will be the nth derivative of e to the x. If I will put the function, the first derivative, the second derivative, the third derivative of the function. Function is just e to the x. First derivative, the same. And then at 2 will be e squared. That means the nth derivative will be e squared over n factorial x minus 2 to the power of n. Okay. But that's, we can see this is also a power series representation for the function, but we will have different interval of convergence for different values. That we can approximate function e to the x by this polynomial, okay? Or I can say series because it's infinity, or Taylor polynomial if I will take the finite number, but it's centered at a different point too. Okay, and I do have this. And of course, I just wanted to make sure that we have this right, like theoretically. Okay, but the e to the power of x at 0 is important. Okay, this one I just wanted to show you different things. Okay, the next one is find the MACLAURIN series for sine of x and prove it that represents sine of x for all of the x, which means we have to use the ratio test, but also we have to prove that the remainder goes to 0, but we will not do it because it's too complicated. Let's just find a new formula. Okay, that's what I have. I have this, the same thing. Yes, you can probably see what I'm doing. The nth derivative at 0, n factorial x to the power of n. Value of the function, value of the first derivative at 0, second derivative, third, fourth, fifth, and so on. Okay, that's me. Let's try to find the derivatives. I will use this, but do not, I will actually make more. I hope I can squeeze my writing. Okay, n 0, 1, 2, 3, 4, 5, 6, maybe 7. Nth derivative, and then nth derivative at 0. Okay, 0 means just the function. Okay, now you have to help me. What is the first derivative of sine of x? Cosine of x. Okay, we have to be careful with this. Now, what's the next derivative? Negative sign. Thank you. You have to watch me because now it's important. Now, again, what's the derivative of this, of negative sine of x? Negative cosine? I think negative cosine, good. What's the derivative of negative cosine? Sine. Okay, I need a few seconds to double check. Sine. Okay, and then can you see what's gonna happen? Because I did start with sine, and then I will repeat this. That means I will have cosine of x, negative sine of x, negative cosine of x, and again sine of x. That means we do have like a cycle of 4. Okay, but now let's find the values at 0. What is sine at 0? Sine at 0 is 0, great. And can you see what's happened? Sine at 0, 0, 0, 0, 0. Every other term actually is gone. What about cosine? What is cosine at 0? Cosine at 0 is 1. But now, negative cosine is negative 1. Cosine, it's 1, and negative 1. That's what we have. Let's see. Because it's not as simple to get the finite, like the sigma notation, okay? But we can at least put all of the values to the expanded form. Okay, that means f at 0 is 0, gone. Actually, this is gone. The second derivative is gone. The fourth derivative, that means every even derivatives are gone. Okay, the first derivative was 1. That means I have 1 factorial x. And then that's 0. I can maybe write for now 0. Okay, the third derivative is negative 1, 3 factorial x cubed. And the fifth derivative is positive 1, 5 factorial x to the power of 5. And then again, negative 1, 7 factorial x to the power of 7, and so on. That means we can see that actually we do have an alternating series. Positive 1, negative 1, positive 1, negative 1. That means my formula looks like negative 1 to the n, okay, because it's 1 or negative 1, 1 or negative 1, over n factorial. Oh, no, not as fast, Kasia. You have to actually tell me. And then I have x to the power of, that means what I need? I need this number and I need this number. That we have 1, negative 1, 1, negative 1. Okay, negative 1 to the n. And now, can you tell me what we have in the denominator? We have 1 factorial, 3 factorial, 5 factorial, 7 factorial, and so on. That we don't really have 1, 2, 3, 4, 5. We have just odd numbers. And do you remember how can we define the odd numbers? This is the very, very first section, like 11.1. Like having n as a counting numbers, how can I define only odd numbers? Somebody remember? No? Like, okay, how would you define even numbers? Maybe we can start with even. Using n, using just n. Okay, like n is simply 1, 2, 3, 4, and so on. That means how can I use n? What I have to like do with n? No, n squared, we will skip some because n squared means 1 squared is 1, 2 squared is 4, 3 squared is, oh yeah, yes, close. Okay, 2n. 2n, this will be even numbers. But 2n plus 1, because o minus 1 will give me an odd number. That means I do have an odd factorial, which I will put 2n plus 1, just because I'm starting from 0. And the same is the power. 2n plus 1. Okay, that means I believe if I will substitute 0, I will have 1 over 1 factorial x to the power of 1. If I will substitute 1, we can see I'm creating 3. 2 plus 1, 3. This will be this, and negative number. If I substitute 2, I'm creating 5. That means this is a power series representation, which of course is the MACLAURIN series for function sine of x. Okay. Oh, something is factorial. I'm sorry, factorial, not to the power of n. 2n plus 1 factorial. Okay, and I believe, do I have the, oh, I have lots of, okay, that's my work, I mean our work, and then I typed something. Okay, we do have all of these formulas. I do have this, right, which that's sine of x, sine of x, right? I think we have this on my slide. Okay, and this is good for all of the x's. We're not gonna really prove this, but this is good for all of the x's, which means radius of convergence is infinity. Okay, sine of x. And we have nice expanded form. Okay, what I have also, I also have the next function that is important is the cosine of x. But what we will do, we will use different, oh, am I there? Can you hear me? Because my internet seems to be like, oh, you can't hear me. Oh, no, you can hear me. And can you see me? Okay, okay. For some reason, like I think, yes, that's what I thought. It paused, yeah. Yeah, I don't know if I was telling you, but I did change my internet for the best one that I can get. And I don't think it's good because I have these moments. Okay. That we know e to the x, we know sine of x. What we will try to do, we will try to do cosine of x, but we will not do the whole table and the derivative. We will try to differentiate sine, because what's the derivative of sine of x? Of course, you can type the answer. Of course, it's cosine of x, right? That means if I will take this function and differentiate, I will get a formula. I can differentiate the expanded form. I can differentiate this right away. I will get the formula for cosine of x. That means let's maybe try. Maybe I can squeeze here. Derivative of sine of x, it's cosine. That means I will try to differentiate this formula. Starting from 0, -1 to the n, 2n plus 1 factorial x to the power of 2n plus 1. But actually, let me try. I need extra slide. 1 second, I will just insert a slide. Okay. Okay, that means one more time. Cosine of x is just the derivative of sine -1 x to the 2n plus 1 over 2n plus 1 factorial. Okay, and let's differentiate. We remember, let's differentiate. That means we have to copy everything what is not x, because that's constant. And we also not changing that, and we will start with 0 because we're not losing any term. If I will switch this, you can see we will differentiate x, and derivative of x is 1. That's we're not losing the first term. We will differentiate x cubed. Derivative of x cubed is 3x squared. Derivative of x to the power of 5, 5x to the power of 4, 7x to the power of 6, and so on. Okay? But let's do this using a sigma. That means I'm copying -1 to the n. I will copy 2n plus 1 factorial. And the only thing that I have to differentiate is this. That's what I was saying. X to the power of 3, 5, 7. Okay, that means x to the power of 2n plus 1, derivative is 2n plus 1 times x to the power of 2n plus 1 minus 1, which is just 2n. Okay, because we're always subtracting 1. Okay, makes sense? I can maybe write this, and we can definitely simplify this a little bit. 0, negative 1 to the n, 2n plus 1, and I think my factorial, I can say 2n plus 1 times 2n factorial. Yes, like we remember one number, the last one, and then one number less. Okay, and then this is x to the power of 2n. And then I can simplify 2n plus 1 to n plus 1. And the final formula for cosine of x, the MACLAURIN series, is sigma from 0 to infinity, negative 1 to the n, x to the power of 2n over 2n factorial. Okay, and also works for all of the numbers. Radius of convergence, infinity. Okay? And you can probably guess, if we will go through the table, the derivatives, only the even numbers will stay, because the odd numbers will be sine. The derivative of cosine is sine. That means every other term we will have sine. Sine at 0 is gone. Sine at 0 is 0, which means the term will be gone. Okay. Okay. That's mean what I have. Actually, I do have the exercise for this, but we will skip this one. Okay, cosine. Okay, we can see cosine, and that's what I did. And we do have a final answer. We can also do term by term, but I did the sigma. We will skip this one. Okay, that means this is the summary page for us. Okay? We have to know the power series representation for just the geometric one, the rational function, x to the n. E to the x looks like that. Sine of x looks like that. Cosine of x looks like that. And inverse tangent was also done through the geometric one. The integration, probably you remember, the integration is 1 over 1 plus x squared. That means we do have x squared to the power of n, which is x to the 2n. You can check the last week video, but yeah, we did this. And you can see this one was done, the first one and the last one was done through the geometric one. That means it's just the interval from -1 to 1 as an interval of convergence. The rest of them works for all of the numbers. Okay, and I will really recommend you to remember these formulas. Okay, we can see, like, based on the denominators, n factorial, 2n plus 1 factorial, it's sine of x, 2n factorial is cosine, and 2n plus 1 without the factorial is inverse tangent. Okay, okay, let's see, because I have also one thing. Oh, okay, that's mean I have like a practice for this. That's mean, what do you think? Do you remember the e to the x we were trying to, okay, I have, okay, all of them. Let's see if we can find the sum. That's mean finding the sum means if we can match with the given formulas. That's mean, let's see this one. This one looks like, can you see, based on the denominator, 2n plus 1 without factorial. That means, do you remember the formulas? Oh, I wish to have the reference page. Let's look at this one, inverse tangent. That means x is replaced with square root of 3. Okay, and do you know the value? Inverse tangent for what angle is square root of 3? I don't know if we can get this. Inverse tangent for pi over 3, 60 degrees. Okay, okay, let's look at, actually, can you tell me this one, number 3? What formula do you recognize? What we have in the denominator? 2n plus 1 factorial, which means is sine of x, sine of pi over 3. Do you know the value for sine of 60, sine of pi over 3? Oh, are you there? Because nobody is responding. Square root of 3 over 2. Oh, can you hear me? Maybe I'm okay, that's good. Okay, but we can see, you can probably pause the video, and if it's too fast, but it's just the previous slide. It's just this 5 formulas. Okay, this one I will say is cosine, but this one I will rewrite as a pi and 3 to the power of 2n. Okay, because we can see we do have 9, but 9 is 3 to the power of 2, and n is there. That means this is cosine of pi over 3, it's 1/2. Okay, I'm not gonna give you hard time. This one, it's like pi to the power of 2n and 4 to the power of 2n. Yeah, the cosine is tricky sometimes. Oh, I missed the -1. Pi over 4 to the power of 2n and 2n factorial. That means it's nothing else like cosine of 45. And I know that you know the value. Okay, this one is tangent, inverse tangent at 1. We can see pi over 4. And oh, what about this one? We did practice this one. We can skip the last one, but what about this one? It's just n factorial. You remember the very, very first formula today? It's e, okay, but it's e to the power of 2. Samuel, is closed, but let's see something. E to the power of x wasn't really the alternating one. That means I have -1 and 2 to the power of n. I have to combine these two numbers. Okay, that means actually is e to the power of -2, because -1 to the n, like for rest of them, is not part of the main formula. It's just x to the power of n over n factorial. That means my x is -2. Okay, that means just, yeah, this is just like the way to recognize the formulas. Okay, let's do one more thing today. I mean, few things, but one concept. That means that's the formulas. Okay, we will skip this. You can check the, we will skip this. You can check the solution. Okay, that means now let's just do one application of the Taylor polynomials. We know what is Taylor polynomial. I will not go through. We have to just simply cut the entire expansion. Okay, that means I will not go through. We know what this means. That we can see, if I want t sub 0, which is just the 0, just the constant. If I want t sub 1, which this will be the first degree polynomial, I have to stop at x to the power of 1. If I want the second degree polynomial, I have to stop at 2. If I want the third one, I have to stop at 3, and so on. Okay, that means that's the polynomials. Of course. Simple, even more simple than the entire expansion. And let's say e to the x, centered at 0, that's we know the formula, and let's just let's just put down the 0 degree polynomial, first degree, second degree, and the third degree. And I can show you, this is the formula, and this is the whole expansion. We can see 3 dots. And now t sub 0 will be just a constant. T sub 1 is just x plus 1. Okay. T sub 2 will be just this, up to x to the power of 2. T sub 3 up to the power of 3. Okay. And now, of course, what we doing? We can approximate a function e to the x using respectively these polynomials. And I don't know if you remember from calculus 1, linear approximation. You remember the linear approximation is just simply a tangent line, which actually the first degree Taylor polynomial is giving me a tangent line. Okay? If we will find a tangent line to e to the x at 0, will be just x plus 1. And we can see what this means. Let's look at the graph. the pink, yes, the pink curve is e to the x. And then t sub 1 is just the line. As we can see at 0, it's quite a good fit. They almost look the same. And then the second degree polynomial is, okay, parabola, the yellow one. Okay, the third degree is the blue one. That we can see as soon as I increase the level, I mean the degree of the polynomial, the function looks more like e to the x. But even the linear function close to 0, we can see if we will zoom in, they all look the same. That means this is the way to approximate exponential function by the polynomials. And we, as I said, we all love polynomials. Easy. Simple for some differential equations, for some programming. Just power function, x to the power 1, 2, 3, 4, 5. Okay? That means that's the way to use it. Okay, let's see a little bit, yes, the values. Okay, the same for this one. Find the Taylor polynomial, okay, which actually I should say MACLAURIN because it's at 0. Sine of x at 0, which is our formula, okay, and find actually the Taylor polynomial degree 5. Okay. And for the sine, since we only have the odd degrees, I think 5 will be easy. That's me. Let's see. Sine of x, that's our formula. Remember, we have to know this formula. Okay. And then sine of x, the same thing, but expanded form. One more time. If I will put instead of n 0, you will get this x. If we will put instead of n 1, we will get this 2, 3, 4. Okay, and now I need t sub 5, the fifth degree polynomial, which means I have to stop at x to the power of 5. Okay? And the same thing, my sine curve could be approximated by the fifth degree polynomial. And instead of like they ask us in the question to approximate sine of 0.03, instead of like having this value and maybe using a calculator, because how can I approximate? I can simply use the polynomial. And instead of x, I can put 0.3 and get the value, which I did here. Probably we still need a calculator, but we can do it even by hand. This one, we can't really do by hand. And let's look at the graph. Yes, we can see the pink curve is the sine. And then I'm like approximating close to 0, almost all of them looks really good approximation because the first degree is just x, just the first straight line. Third degree, which one is the third? The yellow. Can you see? Not really like a sine, but almost like a sine. The fifth degree is the blue one. Yeah, good approximation. The seventh degree is this one. Okay. And we can see almost, that's me, and if I will increase the degree, I will have perfect approximation. Yeah, not having this trigonometric, just having the power function. Okay, but now we will skip this. We have the solution. Okay, we will do one thing, because as I said, we can approximate a function by Taylor polynomial, but we will always have some like a normal approximation, some error, okay? And we have to know how big is the error in this approximation. That means what we will have. Of course, the entire series is the entire sum. Taking the Taylor polynomial, I'm leaving some like margin, like some error. And this error, yes, is simply the entire function minus the entire function minus the Taylor polynomial. And I can just tell you, I can show you the theorem, like how big is this error. And it's quite similar that we were doing for the alternating series test, the alternating series like approximation theorem. That means let's see how big is this error. We will call this Taylor's inequality. We can still use this alternating series estimation theorem, but for this one, we will use Taylor's inequality, which is almost the same thing. That means, let's see. To approximate this small error, okay, we know that this error is less than this big formula. Let me just write one more time the Taylor formula. It's the nth derivative at a n factorial x minus a to the power of n. And hopefully you also remember a little bit from the previous, the alternating series estimation theorem. The little error, do you remember, was always less than the next missing term. Like if I took the sum of 100 terms, let's say, okay, as sub 100, then the error in this estimation was less than b sub 101. You remember? Or like if I took, like, let's say just 5 terms, that means the error in this estimation was less than the b sub 6. If I will take like 9 terms, the error was less than b sub 10. Always the first term that was not counting, that I didn't really count in my partial sum. That means let's look at this box, because this box is exactly the same idea. Okay, having this approximation, I will have this error, and this remainder has the size like this, less than this. It's also like a next term. That means if I had n factorial, I have n plus 1. This is the next one. If x was taken to the power of n, I will stop at n. I will approximate the error by n plus 1. Next number. And even this number m, we just use like just notation m, it's also the next derivative. That was the nth derivative. This will be n plus 1. Okay? Which of course we have to find the maximum value on the interval of convergence, but still is the next term. That we can see n plus 1, and also the next derivative, n plus 1. Okay, that's also quite, yes, important, but it's the same concept, the same idea. That means let's do 2 problems, and we will use this, we will approximate my error, like in my approximation, we will use the Taylor's inequality. We will skip this one. Okay, that means I have this question, and I have next one. They are a little bit connected. And this is kind of like that we may ask you, because it's multiple choice, that means we may ask you on the quiz or final. Okay, that means first question has nothing to do with this Taylor's inequality. Let's see. Find the 3rd degree Taylor polynomial, t sub 3, for the given function. And the function is just different function, not just e to the x. E to the power of 1 plus x over 2, about a at 0. Okay, that's what I will need. And we can see, you can pick, but we have to know the values. Okay, that means this function 1 plus x over 2 can be, okay, approximated by the 3rd degree polynomial. And let's see what we need. We need the value of the function at 0. We need the value of the first derivative at 0, 1 factorial, x to the power of 1, because it's minus 0. We need the second derivative at 0, 2 factorial, x squared, and we need the 3rd derivative at 0, 3 factorial, x to the power of 3. And that's it. And I think everybody can find the derivative of this function, the first, second, and the 3rd, and just substitute to this line. But let's do it together. I will build that table, n, and then this will be a function. Okay, my line is a little bit, okay, oh, and this will be a function at 0. Okay, 0, 1, 2, 3, okay, just 3 for now. Okay, 0 is just the exact function, 1, e to the power of 1, x over 2. I don't know, maybe, hopefully it's not too late. Can you tell me the first derivative of this function? What's the derivative of e to the power of 1 plus x over 2? Yes, I hope we remember this. Exponential function has the derivative of the exponential function, especially the e, is the same function. Okay, it's just e to the power of the same number, but we have to follow the chain rule. times derivative of the inner function. What's the derivative of x over 2? Because derivative of 1 is 0. Okay, what's the derivative of half x? Oh, just half x? Oh, I hope we all there. It's just half. Thank you for saving my question. Okay, that means just times the derivative of the inner function, 1/2. And then I will repeat the same thing. Derivative of this, of the exponential function, is just the same function times derivative of the inner function. That means e to the power of the same thing. I know, looks weird, but it's not, but times 1/2, which I will have 1/4. And e to the power of this times 1/2, 1/8. Okay, now let's substitute 0. If I substitute 0, I have just e to the power of 1. I have half e to the power of 1. I have 1/4 e to the power of 1. 1/8 e to the power of 1. Okay, that means, do you think you can tell me what is the answer? Which one is the correct one? I will start putting this. Answer A. Okay, let's see. Probably. Oh, we have to be careful. Oh, actually, I'm happy that you said so. Because answer A, it's not the correct answer. Let's see what is missing. That means, Samuel, I know, thank you for answer, but this is the common answer, the common mistake, I can say. And please do not repeat this on your quiz or especially on your final. Okay, e at 0, function at 0 is e. We can see, I just copy this number. Now, the first derivative is 1/2 e. Okay, I can put e on the top, but let's see what I also have. 1 factorial. Okay, and then second derivative is e over 4 x to the power of 2. But what I also had in my formula, I have 2 factorial. That means, please remember about these factorials. Yes, that means probably we have to. And the third derivative is e over 8, correct. But I also had the part of the main formula, 3 factorial. That means now we can find the correct coefficient. E over 2, that means this is, yes, that's, we can see this is only 2, which is not, yes, not exactly correct. 2 is 8 times 2 is 8. This is 8 is 48. And it will be again. Maybe should. Okay, enough. We will. And thank you. No. Hopefully. Oh. I just want to answer. Oh, I can't even go. Oh, yes, now. Okay, now, am I back? Okay, okay, that's one more question. Okay, that's you can see this is perfect example how we can get the Taylor polynomial. Okay, we have to find all of these values, and you can see I wrote expanded form of this formula. Okay, let's see the next question. Now, use the Taylor's inequality to estimate the accuracy of this approximation. Yes, just from the question that we did. Okay, that means we have to approximate our given function by the Taylor polynomial, degree 3, which actually is this. Okay, we are approximating the function by this. Okay, this is the third degree polynomial at 0. And now we have an interval of convergence from -2 to 2. Okay, that means Taylor's inequality approximating by the third degree polynomial. That means this remainder, this error, this estimation the error in this estimation is less than this. And hopefully we remember m 4 factorial x to the power of 4. You remember? Because it's the third degree, that means I have to put the next number. And m is the maximum value of the next derivative, of the fourth derivative on the given interval. That means let's find what is the fourth derivative first. And what I will do, I will just jump here, can you see? And I will compute just one more derivative. E to the power of 1, x over 2 times another half, 16. That means derivative is 1 over 16, e to the power of 1, x over 2. And we always take like the absolute value, because if this will be negative, this is my value m. But now the thing is, I have to substitute instead of x a number that will give me maximum value. And the number I can only take from this interval. That's mean, what do you think? Which number, -2 or +2, of course, one of the end, will give me maximum value? Of course, +2. That means I'm substituting +2. Instead of x, I will substitute +2. 1/16 e to the power of 1. 2 over 2 is 1, which this will be e squared over 16. Okay, oh, I don't have enough room. Okay, that's mean I can maybe write here. M is e squared over 16. 4 factorial is 24. And now I also have to substitute something for x. And I can tell you always the x is also, what I can say, it's always the radius of, because radius is the maximum distance from the center to the edge. That means radius is 2, which looks like, yeah, because it's 0, that means looks like the value 2 is one of the end, it's one of the endpoints. But I can tell you always, instead of like the x value, we always have to put radius. That means I will have 2 to the power of 4. Okay, because this is the 2 is the maximum distance that this function is convergent, and this approximation works. Okay, and I think 2 to the power of 4 is 16. I can cancel out, and the final value is e squared over 24. That means this remainder is less than this number, and I see this number here. Okay, that means that's how we can use the Taylor's inequality. Okay, please check. I think I have one more question solved here. You can check here. You can check some other like problems. I think I did open the final exam module. That means it's week 16. You can also check the solutions of some of the sample of the final test. Every single final test, final exam includes this type of question. That means check the question and check my solution. And I think I post like few samples. That means every single final test again includes this question. You can check the solution. Okay, that means that's everything for today, for this week. Good luck with your assignments, and any question you can always email me or use the discussion. Okay, but please, yeah, please work. We still have few weeks. I know that we kind of slow down at the end of the semester, but just few weeks and we will be done. Okay, thank you, and thank you for being with me tonight. Thank you. Okay, thank you.